Well, I want to be able to connect an additional moisture probe to my swarm eval kit for monitoring moisture and levels in the garden. Putting this probe in a different location, maybe averaging the values from the two probes, or maybe even having multiple probes going to multiple parts of the garden. But I got to start with getting two probes out there. And the first obstacle to that is the fact that all of these probes come shipped with the same address on the I2C bus. The address is 20 hexadecimal, which is 32. and they have to have different addresses in order for the CircuitPython program to be able to read data from them. And so unfortunately, there's no CircuitPython program for changing the address. There are Python programs and MicroPython programs for the Raspberry Pi, but what I found was that there are also programs for the Arduino, and I happen to have an Arduino or two. So here I have one hooked up. In truth be told, I've done this before, but I'm going to do it again for you to see. Hooking up the clock line, the yellow line, and the data line here, and also power and ground from the Arduino. And then we want to upload this I2C scanner program to read the address of the probe that already exists, and then later we would run a program to change the address. So I'm just going to upload this program now. So it's uploading. It says it's done uploading. So now I can get the serial monitor. And what it's telling us is that the I2C scanner is scanning, and it's not going to find anything. We're never going to get any result out of it. As I've mentioned, I've done this before. And same thing with the address change program. If I upload it and run it, nope, nothing happens. It just hangs. Okay, and so tried many things. Tried checking all of the jumper cables and the jumper wires and the alligator clip wires, and also I tried changing out the Arduino, and I also used different types of Arduinos, the Arduino Leonardo as well as this Arduino Uno, and no dice. None of those things worked. So some fair amount of trying different things over a couple days failed, and what I finally wound up finding out during investigating forum discussions of the I2C line for the Arduino is that the pull-up resistors inside the Arduino, there are default pull-up resistors, and the information about this probe is that it must have pull-up resistors. So I thought everything would be okay since there were pull-up resistors by default on the I2C line for an Arduino, but maybe not the right values for the I2C line. And why would that be? And all the details we'll investigate next. Well, I found information in the 294-page data sheet for the AppMega 328P about requirements for the two-wire serial bus, which our I2C bus is. And one of them involving the value of the pull-up resistor on the clock pin, the SCL pin, and the data pin, SDA, in cases in which the frequency of the clock is less than or equal to 100 kilohertz, while the default frequency of the Arduino I2C line is 100 kilohertz. We've got minimum and maximum values for that resistance right here. This one makes sense looking at it. We've got a voltage on top divided by a current on the bottom, and Ohm's law tells us that voltage is equal to current times resistance, so resistance is equal to voltage divided by current. The second one might not make sense at first. It's a time, 1,000 nanoseconds divided by a capacitance C sub B. But when you think about the time constant for a circuit with a resistor and a capacitor in it, its resistance times capacitance is equal to time in seconds. And so therefore the resistance is equal to time divided by capacitance. And the C sub B is the capacitance of the bus line itself. Okay, and so in order to figure out what values for the pull-up resistor we should have, should be somewhere in the range between these two values, we're going to have to measure the capacitance of the bus line. And so here I have a piece of bus line that was cut off of the other sensor, the original one that's now attached to the swarm eval kit. And here you can see on my second sensor, this is what that line looks like. I cut most of it off, and we're going to measure the capacitance. We've got a multimeter here set to measure capacitance. It measures in nanofarads. There's no way to change that, so we're going to get a value in nanofarads, which we'll have to convert to farads in our calculations. But anyway, we've got here we have the data line in blue and the clock line in yellow, and the capacitance between those two wires in this cable is the capacitance that we're talking about here, the bus line capacitance. So we've got the data line connected to the black cable coming from the multimeter, and the red cable we're going to touch to the clock line, and we're getting a value of 7/100ths of a nanofarad. So 7/100ths of a nanofarad, well, that's 70 picofarads, and so the requirement up here on the cable capacitance is it'd be greater than 10 picofarads and less than 400 picofarads. So our 70 picofarad cable falls in that limit. And now we just need to calculate these minimum and maximum pull-up resistor values, and have a little Excel spreadsheet set up here. To do that, we need to put in the capacitance in nanofarads here of the bus line, which we saw was 0.07, and we have the 1,000 nanoseconds put in, which gives us a minimum, or excuse me, a maximum resistance value here of a little over 14,000 ohms. Okay, make that stop beeping. Okay, and then our voltage of our system here is 5 volts, so we can put that in and get a calculation of the minimum resistance is a little over 1,500 ohms. So the pull-up resistor should be, for this I2C line to function correctly, should be between 1,500 ohms roughly and, well, let's just say 15,000 ohms. So between 1,500 and 15,000. And so we will hook up the Arduino and do a little bit of measurement on the current passing through the internal pull-up resistor and see what the value of the internal pull-up resistor is. We were wondering if the internal pull-up resistor here in the Atmega 328P is adequate for proper functioning of the I2C bus. And so we need to measure its value, and the way we're going to do that is to just connect a multimeter that's measuring current between the SCL, the clock pin of the Atmega 328P, and ground. And so we'll complete this circuit. We'll have a simple circuit with a 5-volt source in it, and the internal pull-up resistor and our ammeter. And then we'll use Ohm's law here, which voltage divided by current, 5 volts divided by the current that we measure, is going to give us this resistance. Okay, so we have things set up here with the Arduino with the Atmega 328P microcontroller in it, and we're connecting our multimeter between ground here, which is going into the black lead from the multimeter, and then we will touch the input probe here, the positive probe, to the wire here that's coming out of the clock, SCL, the yellow wire here, and see what our current is through this circuit in microamps. Okay, and so we have this set to microamps, and we're going to set it so that it will give us a maximum value. It'll hold the maximum value that it reads here when we touch the input probe here to the clock line, which I'm going to try to do right now. And okay, we're getting a current of 138.4 microamps. Okay, so that's our max. Now we need to do our calculation. We have the 5 volts of the Arduino, and we're going to have to divide by, and we have to convert this 138.4 microamps into amps, so we have to divide by 1,000,000. We have to move the decimal to the left 6 places, so going to be 0.0001384. So we're dividing by 0.0001384. And what we're getting is 36,127 ohms. Okay, that's the value of the internal pull-up resistor. Okay, well, I think we've got a problem here. Well, we saw that we need to have a pull-up resistor value between about 1,500 ohms and about 14,000 something ohms in order to expect the I2C bus to function properly, according to the data sheet for the Atmega 328P. So just experimenting a little bit with external resistor values that we could add. We have the internal pull-up resistor here. We can add an external resistor to our system here and change the net resistance of the pull-up resistors since they're in parallel. And so if we were to use a 20,000 ohm resistor, we would get a net resistance under the 14,000 ohms. We get almost 13,000 ohms, and according to the data sheet that should function. So we've set that up here. We've got a couple 20,000 ohm resistors hooked up here, going from each of the I2C bus lines, the clock line here, a 20,000 ohm resistor going to 5 volts, and the same thing here for the data line. You got a 20,000 ohm resistor going to 5 volts, the 5 volts being supplied by the Arduino itself. And then we've hooked up our probe here, and which we had seen earlier hooked up but unsuccessful, so none of the programs that were supposed to be able to scan the I2C bus for addresses of devices on it or change the address of a device, none of those would work. They all just hung and nothing happened. So we'll see what happens now. We're going to load the scan program here. Which is right here, the I2C scanner program. We're going to load that into the Arduino. Okay, it's uploading. It's done uploading. So should be able to look at the serial monitor now. Oh, we got stuff coming up here. Something's happening. We've got I2C device found at address 0x20. Well, that's hexadecimal 20, which is 2 times 16th. It's 32. That's the address, that the default address of the moisture sensing probe. So Now the program is working, it's finding that device and reporting its address. Okay, so now all we need to do is run the, instead of this, run the program to change the address, which is right here. It's the change sensor I2C address program. And of course we want to change it to, well, it's at 32 now. We want to add 10 to that to make it 42, naturally. And so we want to change its address to 2A, hexadecimal or 42 decimal. So we'll load this program. And uploading. It's done uploading. We need to start the serial monitor to see any results here. And we have device found at 20. Now we're done, and let's see, so we should be getting, we're not getting the result we hoped for there. We should have the address now being 2A. So let's see. What did, oh, I did not change this. This value here has to be 2A. And now it's 2A. Okay, I changed the printout saying it's going to change the address to 2A, but I didn't change the command that is supposed to set the address to 2A. So now we'll upload this. Done uploading. Now we're getting the device address. It was changed to 2A, to 42. So yay! Everything works now that we have a net pull-up resistance within the tolerance specified in the 294-page data sheet for the ATmega 328P. And this much larger of a resistance here is going to give us a value that's too big. But the bigger the pull-up resistor value, the better, as long as the I2C bus functions, because that chokes down the current coming out of the I2C bus. And the smaller the current, of course, the better in general for the functioning of all these devices. So it works. We're done.